Hello, Algebra 1 students, and welcome back to Topic 9. This is our factorable quadratics unit. Last class, we learned how to graph quadratic equations that were in this form right here, that a times x minus p times x minus q, and we called that intercept form. Well, what we're going to do today is really work backwards. Instead of graphing from an equation, we're going to see a graph and see if we can write the equation. So we really have two practice problems to start off today. There's one on the first page, one on the second. And we're going to kind of build some good understanding of what makes up that intercept form equation. So I think really the best way to get started is to jump into it. We have problem 1 here where we have been given this nice quadratic. You can see mine in blue, yours is probably in black unless you have a color printer. And I'd like you to just try and work through the questions. And as you get stuck, unpause and see what you can do. We're starting with A, then you're moving to B, C, D, and then E to finish things off. So, let's see what you can do. Ready, set, go. Now, this first part, part A, is really a blast from the past, right? We learned this in topic 7 when we first learned HK form and the idea of a parabola and quadratics in general, right? So the parabola is the U-shaped graph we make. The quadratics are the actual equations. And part A asks us to write the equation in HK form. So it seems to me like we have a few blanks here. We're going to have to fill in A, H, and K into our equation down below. A is the one where we start at the vertex. In fact, we should probably label that vertex up here. This is the point -1, -9. And A tells us, and then we always have to write it over 1, how far up and over 1 we go to get to the next point. So over 1 is going to be kind of right here and here. How far up do you go now? Well, it looks like you go up 1 in each direction to get to a nice point. So it looks like if we went the other way, we rise up 1 and run over 1. Rise over 1. Okay, you could also just write that as 1. Easy enough. And I know that was kind of a weird way to explain slope, but I think you'll be all right. And then the rest of HK is, of course, remembering that HK is actually the vertex. So we're going to go ahead and put this vertex in -1, -9, except what's always the case for HK form, you do the opposite of H. So if there's a -1, it's going to look like a +1 in our equation, and then a -9. And so our final HK form here would be 1 x plus 1 squared minus 9. Don't forget we do need that squared in the equation, otherwise it would make a line. The square is what causes it to become a parabola. Alright, moving on to B. What are the x-intercepts of our parabola? Write them in xy form. Since eventually we're going to be writing intercept form, and we know intercept form has to do with the x-intercepts, it's always a good idea to identify the x-intercepts. We have the point 2, 0, and the point -4, 0. Would you agree that those are our zeros, our x-intercepts for the graph? So -4, 0, and 2, 0. Alright, so we should be able to write this parabola using intercept form. Intercept form, as a reminder, is going to have that a, that kind of slope, that value that affects the slope of the graph. And x minus p times x minus q, where p and q are really just placeholders standing in for specific numbers. My first question is, how come this equation is incorrect? Well, I mean, the a value, right, is 1, and that is correct. We know it's correct because we use the same a value over for our HK form. But what about the x minus 4x plus 2? That seems to be correct, right? We have a -4 and a +2. Well, don't forget that one of the advantages to intercept form is it's very easy to find the x-intercepts. So let's actually take a quick second and find those x-intercepts. To find an x-intercept, we always replace the y with 0, like so. And then, when we're in factored form, which we are, we can solve. We solve by making two smaller equations, x minus 4 equals 0, or x plus 2 equals 0. And then we actually end up solving, right? So we add 4 to each side. Over here, we'll subtract 2 to each side. Nothing too terrible. Cancel, cancel. And it tells us that the x-intercept is +4, and the other one, -2. Okay. Well, does that match? Is my x-intercept +4? Is my x-intercept -2? And I think you'll find that no, they don't match here. Huh. Well, then that means this is incorrect because there's something wrong with this inside piece. So what's the correct intercept form? Can you see it? One way you could deal with the correct intercept form, though this is kind of a convoluted runaround way, we might as well get a in here, we know a is 1, is you can go through and start with your x-intercepts. We know these two guys are the x-intercepts. And we know our x-intercepts are x equals -4 or x equals +2. We can see that from the graph. And then, because we want the numbers to be on the same side as x, we can actually add 4 to each side. And I know this is strange. It's like we're going backwards here. And this is going to give us x plus 4 equals 0. And same thing if I subtract 2 to get this to a 0 on this side, x minus 2 equals 0. Then we should be able to see our factors, right? Because whatever our x-intercepts were, they're created by setting the factors equal to 0. X plus 4 and x minus 2. Of course, the more astute of you might notice that really all we did is we took whatever the x-intercept was and switched the sign. Right? Same thing over here. And we switch that sign because when we solve, you end up doing the opposite and it flips it back. Alright, let's finish this off. We're going to go ahead and show the math to prove that the x-intercepts of each equation match your graph. This is something that we did way back in topic 7, and we're doing again in topic 9. So we have HK form and intercept form, and I'm going to write each of those. I'm going to go ahead and I'm going to drop the f of x notation and switch to y just to make things a little bit more clear. And also, I'm not going to write the 1 out front. We don't need to, so it's y equals x plus 1 squared minus 9. Save a little space. Same thing for intercept form. That's right above. I'm going to again drop the 1, and it's just x plus 4 times x minus 2. Our goal is to find the x-intercepts for each of these, and we know how to do that. To find x-intercepts, we're going to go ahead and replace the y with 0. I don't know how much room I'm going to need, but I'm going to assume that I'll need 2 columns here, so I'm just going to do 0 equals x plus 1 squared minus 9. And then remember, if you have an equation that only has one appearance or one instance of x, like there is here, then you can think of every other number in here as being attached to x, and we can work through and just follow SADMAP, right? Nothing too bad. So there's a few things attached to x. There's a 9 that's subtracting. There is a 2, which is an exponent. And then there's this 1 that's adding. But at least for now, this 1 is trapped inside the parentheses, so we have to get to that last. Let's work top to bottom and undo the subtraction first. So we end up with 9 equals x plus 1 squared. We took care of the subtraction. Now it looks like we have to take care of the exponent by square rooting. We do need to remember that when we square root a number, when we introduce a square root, we do need that plus minus notation in front of it. Square root of 9, of course, is 3. And I did run out of room here, so I'm going to rewrite up here. Plus minus 3 equals x plus 1. So let's go ahead and isolate the x, and now we can actually get to the plus 1 that was in the parentheses before, because there's no more parentheses. We need to subtract 1 from each side. And don't make the common mistake here where you think you can just do 3 minus 1, which is 2. This isn't 3. This is both positive 3 and negative 3. So what we do is we either put the negative 1 in front or at the back of the plus minus 3. It doesn't matter where. I typically move it to the front, and we get something like this. So to make sure our two x-intercepts are accurate, one x-intercept will be negative 1 with the positive 3. Negative 1 plus 3 is 2. We can notice up here I did get an x-intercept with an x of 2. And my other one will be negative 1 minus 3, which is negative 4. And that checks out. Alright, if we wanted to check intercept form over here, and we pretty much already did this up above, but it's worth reminding yourself of how to do it. We'd start the exact same way we did with HK form. You replace the y with 0. You do every time you want to go ahead and find x-intercepts. It gives us x plus 4 times x minus 2, and then since we're already in factored form, the work is pretty easy here, isn't it? X plus 4 equals 0, or x minus 2 equals 0. And since we reverse engineered this earlier, this better be correct, right? So we're going to have to add 2 to both sides and subtract 4. Those cancel, and we end up with x equals negative 4 or x equals positive 2. Now, notice that I didn't really do SADMAP for the original part here, not until the very end, because we only do SADMAP to equations that have a single x, a single appearance of x. And this equation had two different x's. So we needed to go through and create smaller equations that only had one x in them. Once you're down to the 1x, then you can start doing things to both sides. But we had to use that zero product property to get there. Okay, so we did a nice job of writing both an HK form equation and an intercept form equation from the given parabola. Let's try one more. Alright, a parabola is given to you below. Use it to answer the related questions. So again, you should go through, try all of this, and if you get stuck, unpause and listen to me. Ready, set, go. Alright, well they jump us right into this right away. So they say, what's the intercept form for this parabola? Well, intercept form relies on the x-intercepts. So we have 1, 0 and negative 3, 0. But as we've seen before in the equation, you're going to end up changing those signs. So we're going to have an x with a plus 3 and an x with a minus 1 to take care of the two x-intercepts. Then we need to go through and find the a value. Now, our a value tells us where the next point is, maybe not even a nice point, and our a value always has to be written over 1. So the most we can go to the right is 1. We have to go exactly 1. The up and down can change. So if the most I can go to the right is 1 from my vertex, and we'll label that vertex even though we're not going to use it for this one, negative 1, 2, the most that I can go is, well, to this point right here, because that's how far over 1 it is. So the question becomes, and I'll zoom in so we can see this, how far down and then how far over? Well, looking at this, that looks halfway down, doesn't it? So I think we can say that you go down, and because we're moving downwards, we need a negative, and then 0.5. You could have also written this as negative 1/2 over 1. That's fine as well. So down 0.5. Now, the problem, though, is I'm not exactly sure that that's 0.5. What if it's 0.6 or 0.55? And we want to be exactly correct. Okay? So are you sure about your a value? In this case, I'm not sure. Right, it looks like negative 1/2, but it could be negative 0.6 or negative 0.55. Yeah, we're not quite sure. So what we're going to focus on for this page is how we can make sure the a value is actually correct. So the first thing we're going to do is we're going to choose a point on our graph. And we're going to choose a point that we haven't used in the equation so far. In my equation, I've already used the x-intercepts. So what are some other points? Well, I actually don't see any other nice points here or here. Oh, what about the vertex? The vertex is a nice point, isn't it? Negative 1, 2. Yeah, let's use that point. So we're going to go ahead and choose the point negative 1, 2. In this case, this is the vertex. Now, we're going to take this vertex and we're going to substitute it into our intercept form equation. So I'm going to rewrite the intercept form equation down below. We had y equals negative 0.5, and then two sets of parentheses, and I'll double check those right now. It's x plus 3 and x minus 1. Alright, so as we go through here, we're going to go ahead and replace all the x's with negative 1 and all the y's with positive 2. So the y is 2, negative 0.5, and then the x's need to be replaced with negative 1. And remember to check to see if something is a solution, the left side better equal the right side. The nice part is the left side is stuck at 2, so let's try the right side. We have 3 minus 1, that's 2. We're doing PEMDAS. This is what's in the parentheses. Okay. And then we have to just multiply each of these. I'm going to do the 2 times negative 2, which is negative 4. And then to finish this off, we have to do half of 4, which is 2, and a negative times a negative is a positive, so it leaves us with a positive 2. So that tells me that I'm pretty sure I'm right about my a value, right? I tried another point on my graph, and we got the left side equal to the right. So that's pretty good. Now, what if, though, the a value wasn't actually negative 0.5? What if when we did the math it was negative 0.61 or something? And we wouldn't see that, but we would see the left side doesn't equal the right. Okay, well, let's see how we could do this algebraically. And I'm going to go ahead and do the same thing as before. I'm going to use that same point, negative 1 comma 2. Except this time, I'm going to use an incomplete equation. Right? My incomplete equation still has a here. This is basically saying we're not exactly sure what a is, so let's leave it. But I'm going to do the same thing that we just did. I'm going to go through and replace all the y's with 2 and all the x's with negative 1. And when we do that, now instead of the left side equaling the right, now I have an equation where I don't know the value of a. And I think if I simplify this equation using our awesome algebra skills, we'll probably be able to isolate a, and that will tell us what a has to be to make the left side equal the right. So let's try solving. Right? The first step in solving an equation is simplifying an equation, and when we simplify we use PEMDAS. So I'm just going to show all my steps once more right here. Let's simplify those parentheses that are attached to that a right here. 3 minus 1 is 2. Negative 1 minus 1 is negative 2. And as we did before, 2 times negative 2 is negative 4. So what I have here is 2 equals a times negative 4. And I don't think there's any reason why I couldn't switch the order here and do negative 4 times a. That's the same thing as a times negative 4. Okay. How do we get a alone now? If I want to know the value of a that makes the left side equal the right, I need to get rid of that pesky negative 4 that's attached by multiplication. And I think we do that with division. This will tell us then that a is the fraction negative 2 over 4. Or if you want simplifying, isn't that negative 1/2? Or if you use your calculator, negative 0.5? And so what we've done here is just by filling in the pieces we were 100% sure of, the x-intercepts, and then using another point on our graph, we were able to find the correct a value. This is also very useful if you don't have a graph. If you don't have a graph and you can't count between the points, then it makes finding the a value a little trickier and you'll have to use this method. Alright, does our answer from part D confirm our hypothesis, our guess from part A? Well, on part A, we guessed at our slope, and I would say, yes, it does. If you didn't guess negative 1/2, then it didn't, right? Yes, a equals negative 0.5. Smiley face. Alright, so speaking of not having a graph, let's flip to that third page and see what happens if we don't have a graph. Okay? Part A. A parabola has an a value of negative 2 with vertices at 2, 0 and 4, 0. What's the equation? So looking at part A, you might be tempted to use HK form because oftentimes HK form is a really easy to write way to write an equation. For HK form, you need the a value, and then what else do we need for HK form? We did this one earlier, didn't we? I think for HK form, we also needed the vertex. And unfortunately, looking down here, I don't see the vertex, right? This says vertices. This really should say x-intercepts. Okay, so x-intercepts at 2, 0 and 4, 0. Well, if you're given x-intercepts, and this should make sense considering the unit we're in, we're going to be using intercept form. So let's go ahead and create intercept form with this guy. Now for intercept form, we have that y equals a. I'll fill that one in just a bit. Then there's going to be an x and an x. Now the nice part is they gave us the a value. They said a is negative 2. Sweet. Now our x-intercepts 2, 0 and 4, 0. Well, we just have to switch the sign, x minus 2 and x minus 4, and I think we're done. This would make our correct parabola. Let's try another. A parabola has zeros at x equals negative 3, x equals 1 with an a of 2. What's the equation? Well, don't forget that zeros really just means x-intercepts. We've learned that before. That's what happens when you set the equation equal to 0. So I think my equation is going to be y equals 2 times x with a positive 3 and x with a negative 1. Alright, let's try another one. A parabola has an a value of negative 2 with a vertex of 3, 2. What's the equation in intercept form? Well, they asked for intercept form, Vertex form would be really easy, right? But intercept form can be a little more challenging. So the hint says sketch a graph, so I guess we should probably pay attention to that hint. Vertex is at 3, 2. That's over here. 1, 2, 3, 2. Okay. And then it says the a value is -2. So if my a value is -2, really it means go down 2 over 1 from the vertex. So what happens if I do that? If we go down 1, 2, and then over 1, we get a point here. And then I think I can also go down 2 over 1 the other direction to get a point here. So I actually have a rough sketch of my parabola. It's going to look something like this, right? Okay. How does that help us? Well, I think actually, doesn't this show us the x-intercepts here? It looks to me like this x-intercept is the point 2, 0, and this is the one 4, 0. And that really cracks this case open because now I know the a value is -2. One x-intercept is +2 and one is +4. Of course, reversing the signs to get our intercept form equation. Okay, let's try another. Parabola has this vertex and an x-intercept at -3, 0. Huh. Well, what do we know about my equation so far? We don't know the a this time. We know an x-intercept, but we know parabolas always have 2. So it seems like I'm missing 2 pieces of information. Oh, hint, sketch a graph. Okay, let's listen to that again. So -2, -3 is down in that third quadrant over here. So we have -2, -3 right here. And then they also told us we have an x-intercept at -3, 0. That's up here. Well, through symmetry, right? Remember that axis of symmetry that goes through? I think we actually have a pretty good idea of what my parabola looks like. Because if there's an x-intercept here that's 1 away, there has to be one on the other side too. So that other x-intercept looks to me to be -1, 0, so x plus 1. That's good. But what about that a value? Well, as long as we didn't go more than 1 over, I think we can just count up 1, 2, 3. Same thing over here, up 3 over 1. And so my a value is 3 over 1, or just 3. All right, 2 to go. A parabola has x-intercepts given there, sweet, and it's also known that there's a point on the graph at 2, 36. What's the equation of the parabola in intercept form? Well, let's start with what we know. We know there's going to be some a value, not sure of that yet, and it's got to be x plus 2 and x minus 5, right? These are the ways with these comma and curly braces here. That's how we write multiple answers for x. I think we're missing the a. And it didn't give us a hint here to graph. And I think if you graph, you're going to not be super lucky because this point is just going to be so high up that it's not going to be accurate enough to find the a value. Instead, let's use what we did on the previous page, and let's use this point to find the a value. We're going to say we don't know the a yet. Okay? But we're going to go through and use 2 and 36 to substitute in to find a. The y is 36, the a is unknown, and the x in this case is going to be 2. So let's take a look. X is 2. This leaves us with an equation with only one unknown, the a, so we want to isolate a. Before we do that, I always like to simplify. So we end up with simplifying 2 plus 2 to get 4 and 2 minus 5 to get -3. And then we're going to go through and actually do 4 times -3. That's -12. And now, what's attached to a? Well, -12 is multiplying, so let's unmultiply with division. And we have to do 36 divided by -12, and I happen to know 12 goes into 36 3 times, and a positive divided by a negative is a negative. And lo and behold, we find that a is the value -3. And so our final equation will be -3 for a, and then those same x-intercepts as before, x plus 2 times x minus 5. Knowing that, let's see if you can recreate the same process over here. Same idea. Give it a shot, then unpause once you get there. Ready, set, go. Alright, hopefully you had some success. The setup is very similar, and I'll zoom in so we can see it. We don't know a. However, we do know this is x plus 1 and x plus 3. Okay. They also give us a point, but they wrote the point in function notation, which you might not remember. Don't forget that in function notation, this is your input, and this 2 over here is your output. And so another way to do that is to say the input is -5, so that's the x, and the output is 2. So let's substitute everything in. That means that the y is 2. We don't know the a, but then we also know that the x is -5. So filling this in, like so, we can now isolate a. Let's simplify first. -5 plus 1 is -4. This will get us -2. Okay. Multiplying, this gives us +8. And the last step is the same again. We want to divide off that 8. Okay. So this gives us an a value of the fraction 2/8. If you divide by 2 to simplify, it could also be 1/4. Or if you used your calculator here, it ends up being 0.25. So our final equation, I'll use the 1/4, but you can use any of those. We had x plus 1 and x plus 3. Not too bad. All right, and let's move on to that last page. And this last page consists of 2 word problems, but not to scare you. I know a lot of students will see word problems and go, oh my gosh, it's going to be the worst thing ever. And it's really not. It's going to practice all the same skills that we've done on the previous couple pages. They're just going to add context to our equation, where context is usually discussing what the 2 variables mean in the problem. And with giving those variables meaning, we're going to give the numbers meaning in the problem too. But there's nothing else that's different. You'll find that quadratics are very often used to model motion, whether an object is moving up and down or side to side. We're going to discuss that motion kind of halfway through the problems, but let's just jump right into the problems first and see what we're being told here. Problem 1. A hovercraft takes off from a platform. Its height h in meters is given t seconds after takeoff. This is modeled by the equation h of t equals negative parentheses t minus 11 times t plus 3. All right. Part A. Interpret the meaning of h of 2 equals 45 in the context of the problem. Your answer should reference the height of the hovercraft and the time in seconds. All right, so let's break this down. H of 2 equals 25. Do we see what each of these numbers means with the original equation? Right, h of 2 means the t value was 2. Okay, so I'm just going to write this out quickly. We know that when t was 2, what happened? Well, when we did all the math with 2 plugged in, that told us that the answer, and the answer h of t, h is going to be our answer, tells us that h equals 45. All right, let's actually interpret that answer. All right, t equals 2. What does t stand for? T is seconds after takeoff. So I think we could probably put all that together, right? So we'd say 2 seconds after takeoff, right? And this is occurring right at 2. We substituted in 2. So we're saying 2 seconds after takeoff, what happened? Well, 2 seconds after takeoff, we should probably talk about the hovercraft, since that's what the equation is for. The hovercraft is what? Well, I think we have this 45, but 45 what? It's always nice to include units. Is 45 h in meters? Oh, okay. So it's 45 meters above the ground. And that's it. When you interpret a problem, you want to incorporate all the numbers that are available. And our numbers in this case are an input and an output. So if you explain what the input and output mean and how they're related, you're good to go. All right, let's look at B. Find the value of h of 0. What does that tell us about the hovercraft? Okay, well, we know how to find h of 0. H of 0, just jumping back to our equation again, means we're doing h of 0, means you're replacing the t, and I'll try to keep my colors consistent here, you're replacing the t with, not 2, with 0. And so, in my equation, I'm just going to replace everywhere that I see a t with 0. Okay. This time I'm just going to keep the h of 0 out front, hopefully switching back to that black color here. There we go. And we're just going to simplify what's in our parentheses, right? PEMDAS is that simplification. So we have negative 11 and positive 3. Okay, so h of 0 one more time. Negative 11 with another negative makes it a positive 11, and 11 times 3 gets us 33. Okay, so this one says 0 seconds after takeoff, the hovercraft is 33 meters in the air. Which is kind of weird, because if it hasn't taken off yet, how could it be in the air? And there's a couple interpretations here. Well, maybe the height in meters isn't necessarily how high it is in the air. Maybe it's just on a platform that's 33 meters above sea level, right? Because it could be possible that you have this elevated platform, or if it's taking off on the top of a building, that it's already above the ground. It doesn't necessarily have to be in the air. I guess I just added that part. Right? The other option too is this, well, no, let's just go with that. We don't need to overcomplicate this. All right, part C. When does the hovercraft land, and how do you know? Well, I think what we should probably do then is maybe sketch a bit of a picture here to understand what's going on, and we'll include the math that goes with the picture. Okay, so if we're going to include a picture of a parabola, we need to find all those usual things for the parabola. We already know the y-intercept, right? We found that on part B. When you substitute 0 in for the input, that gives you the y-intercept. I think we should also probably find the x-intercepts. In this case, though, these are using t as the input, so I'm going to find the t-intercepts. And to do that, that's when you replace the output with 0, and you have our factored form equation set equal to 0. Okay, to do this, we solve each equation, right? We set our factors equal to 0. We've done this once or 100 times so far this unit. And we solve. And hopefully at this point you're comfortable finding that t is 11 or t equals negative 3. Okay, let's just take a real quick look at this picture then. I'm going to go ahead and sketch some axes here. You'll notice that I'm not really giving, too much space to this negative side of the axis, because my output axis, my y-axis, is the height. And I think it doesn't make much sense to consider negative heights down here. Alright, however, the time axis, I did go over to negative 3, and we're going to talk about how that doesn't really make sense. And I should go much smaller in terms of my tick marks, huh? So here's negative 3, and then we have to go out to 11. That's why I said it'd go smaller. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 over here. Cool. Alright, so we have those two. Now we have two options for this parabola. Either the parabola can go down like so, or it can be facing in a downwards direction and go up like that. And I think it's going to be in a downwards direction, that second one, because my a value is negative 1. We also know, though, that h of 0 is 33, and we know that h of 2 is 45. So I think my y-axis has to go up pretty high here, right? Maybe I can just go 10, 20, 30, 40, 50, put 50 up here, and then I'm just going to approximate, right? This is a rough sketch so that we can understand what's actually happening in this picture. It doesn't have to be perfect. H of 0 is 33, so I'm going to do the y-intercept in red here. 33 is about right there. And h of 2 is 45, so 2 comma 45 is somewhere up here. I think this gives us a pretty nice picture of our parabola, and again, kind of this rough sketch up here does something and eventually comes back down, right? Now, we need to understand too, and this is a little bit of a conceptual trick here, that my hovercraft is not actually flying up at an angle and then flying back down. We usually use these quadratic equations to just model objects that go up and then go straight back down in that same line, or that move to the right and then come back left. Okay? The reason that the picture looks like a parabola is, think about if you throw a ball. Right? If you throw a ball straight up in the air, the ball doesn't go up at a constant rate. As soon as you throw the ball up, right, it's going up really fast. But then, as it gets closer to the top, it slows down, and now it starts to come down, and it picks up speed and goes fast at the end. That's kind of like our parabola, where our parabola is really steep at the beginning, but then it slows down, slows down, slows down, and actually it technically eventually stops. It flattens out, and then it starts to go back down and picks up speed, picks up speed, picks up speed. So honestly, this probably is not a great model for a hovercraft, because if the hovercraft goes up really fast and then slows down as it gets to the top, and then when it's coming down, it picks up speed till it lands. You usually don't want something to go really fast right before it lands. But either way, here we are with our hovercraft doing some weird landing stuff. Now, it says when does the hovercraft land? Well, I think we're going to assume that it lands when its height is going to be 0 meters in the air. Where is the height 0 meters in the air? Well, one of them is this point over here when t is -3, right? This is our point, -3, 0. But in fact, I think in this case, the -3 doesn't make a lot of sense because that'd be -3 seconds before takeoff. What usually happens when you have negative numbers in a real world situation is we say we don't really pay attention to those. We really just want to focus on the graph that starts at the y-intercept with positive t values. So is there any other spot where the hovercraft is at a height of 0? And yeah, of course, it's our other t-intercept here. Okay, so the hovercraft, always good to finish with a sentence, lands at t equals 0, nope, sorry, at t equals 11 because the height is 0. All right, what about part D? At what time is the hovercraft at its maximum height? Well, visually, right, we can take a look at this parabola here. The maximum height is the highest it gets. And the highest it gets, I think another name for that is probably the vertex, isn't it? Now, my vertex was not exact. I just kind of threw some points together and dropped it back down here. It's probably not even right. But we know how to find the vertex. We've done this the last couple days. We know the vertex appears exactly in between our two t-intercepts, in between 11 and -3. So this question is actually asking for the vertex of the equation, and we're going to go ahead and create the vertex. We know the h value of the vertex, which is like the x, occurs exactly in between the two x-intercepts. So I'm going to take the -3 and the 11, add them together, and divide by 2. That's 8 divided by 2, which is 4. Now that we have the h value of the vertex, right, we know, and I'm just going to add to this point over here, that this is going to occur at 4, comma something. 1, 2, 3, 4. That was pretty close, between 4 and 5. We need to find the k value, right? Our vertex is always h comma k, and our k value is easy enough because whenever you have an input, what do you do to find the output? Well, you substitute it into the equation. We need to find h of 4. Okay. And to find h of 4, we have this equation, right? Negative something like this. This is a +3 minus 11, and we need to substitute in that 4. Okay. And we're just going to go through and simplify here. H of 4 is negative. This will be -7 and +7. That's nice. And I'll just work to the right so I can keep my space at the bottom. 7 times 7 is 49. 2 negatives make a positive. I'm looking at a k value of +49. And actually, that was pretty good. A little bit above 50, but not too bad. So, at what time is the hovercraft at its maximum height? So we'd say at, I'll keep my colors here, we'd say at t equals 4 seconds, right? The hovercraft is at its max height of, and we found 49 meters. I would say these are probably the two more common questions that are asked. When does something land? And so you're looking for those x or t-intercepts. And how high above the ground does it get? Okay, so let's try one more example, and honestly, you guys can probably go ahead and tackle this one without me. We're going to do this one a little faster too, though, no graphing this time, I think, maybe till the end. So let's see what you guys can do here. Hopefully you gave it a shot. A diver jumps into the pool from a diving board. Their height h in meters is given t seconds after jumping. This is modeled by h of t, and that's similar style equation. Okay, let's find h of 2 first. So h of 2 equals negative 5 times 2 plus 1 times 2 minus 3. Okay, I'll just work to the side here. So we get negative 5 times 3 times negative 1. 5 times 3 is 15. Two negatives make a positive, so we get 15. Okay. So after 2 seconds, the diver is 15 meters above the ground. All right, how high above the ground is the diving board? How do you know? Well, that's an interesting question, but I think we can answer it just by realizing that the diver is on the diving board how many seconds after jumping? Well, hopefully the diver's not back on the diving board any seconds after jumping, because if they jump up and then they land back on the board, they really haven't succeeded in jumping into the pool. So I would argue that the diver is on the diving board 0 seconds after jumping, right? It's before they've jumped. So I think this is just a fancy way for us to find h of 0. And so this will give us negative 5 times 0 plus 1 and 0 minus 3. Okay. And as we go through and do this, we're going to get negative 5 times 1 times negative 3, which is 15. Okay. So what's actually interesting here is that we ended up with the same answer for both of these. However, that's okay, because parabolas have symmetry. And so I promised you I wouldn't draw one, and now I'm going to draw one anyways. Basically what's happening is the diver's starting at 15, right? And technically they're jumping just straight up and then just slightly off to go straight down into the pool, but that's modeled by a quadratic. It's going to go up. Eventually it has to get back to 15 again before we get down to the ground, right? If a diver starts some height, but they jump up, then their body has to come back down to that height before they get to the pool. Okay. Part C. At what time is the diver at their maximum height, and what is their maximum height? Well, we've done this before. The first thing we need to find is the h value of the vertex. Okay, so we need that h value. This is our vertex again, right? If you think of that picture, the highest point will be over here. So our h value is just found in between the two x-intercepts. Well, wait, I haven't even found the x-intercepts yet. Bummer. I'll just take the space up here, though. Ha! X-intercepts are found by setting 0 equal to the equation, which is different than substituting in 0 to the equation. Okay, so we get t plus 1 equals 0, or t minus 3 equals 0. And solving, we get one intercept at negative 1. That one doesn't really make sense in context of the problem. And the other at 3. Okay, here we go. So our h value will be negative 1 plus 3 divided by 2. That's 2 divided by 2, so that's 1. So this is, by the way, a t value. That's the time the diver is at their maximum height, at 1 second into the jump. However, how tall do they actually get? Well, that is, of course, our k value. And so we're going to need to take that, and we're going to find h of that time of 1. So negative 5, it'll be a plus 1, a minus 3, and I'll fill this in right here. So h of 1, 1 plus 1, 1 minus 3. And so we end up with negative 5 times 2 times negative 2. And we end up with negative 5 times negative 4, which is positive 20. And so this is the max height. After 1 second, the diver is at its maximum height of 20 feet above the water. 20 meters, sorry. Okay, last but not least, what values of t make sense for this problem? List these values of the domain, and how do you know? Well, I think in this case, we're going to get a good clue up here. So I think negative values don't make sense because the graph just doesn't apply over here, right? It doesn't make sense. Maybe you say, oh, the diver's climbing up a ladder, but that's going to be a different rate than them jumping. So almost always in these problems, you're going to see that t will be greater than or equal to 0, right? We're going to start our exploration or our observations right at a time of 0. And then we're also going to stop observing the diver at some point. I think we're going to stop observing when they hit the water. When they hit the water, you could definitely make the argument, well, you could actually go negative height because you go into the water. You're right, but then their speed, which is being plotted by this graph, will be different, right? As soon as they get into the water, they like slow down, and our graph is going to do something weird, right? They bottom out, and then they come back up. That's no longer a parabola, right? Maybe it's like two parabolas put together. So typically, we're going to stop observing when they hit the water. So t is greater than or equal to 0, and t is less than or equal to 3. Now, the other way, there are a couple ways you can write this. We could say this is the domain, and I would accept that. You could also say that 0 is less than or equal to t, which is less than or equal to 3. That's great as well. Or you could even use your interval notation, and you could say we're going from 0 to 3. All right, well, thank you so much for tuning in today, and hopefully we had a pretty clear idea on how to write and interpret these equations. Next class, we're going to bring everything back together again, and we're going to talk about the second part of this goal, which isn't just graphing quadratics in intercept form, but also graphing quadratics from standard form. We haven't really talked about how to do that yet. So there's only 2 lessons left in this unit. Thank you again for hanging out with me, and I'm excited to have you back next class.